they play a very vital role in the economic development of a country. And I think, as all of you are aware, bridges are one of the most visible features of roads and railways. And in the last 3 to 4 decades, the public anywhere in the world want to have a bridge that is aesthetically pleasing and also enhances the environment by its presence. So this has led to the involvement of architects in design of bridges, and I welcome that. But for us in ARUP, as Lauren knows, we have always had a holistic approach to design of bridges, where the form and the function are integrated to create an aesthetically pleasing bridge, which also takes into account the client's budget and is also hopefully easy to inspect and maintain. So what I'm going to do is to speak about a number of bridges that I've been personally involved, where the form and function has come out of the requirements for that particular site. So the first thing, of course, is what type of bridge. And as all of you engineers know, there are basically 5 forms that we can use. So there's a girder, a truss, an arch, a suspension, and a cable stay bridge. So any bridge is either one of these, or it is some sort of combination of these forms. So the form and function then depend upon their location, and I'm going to describe like 7 bridges, ranging from very small bridges to fairly large bridges. So there are 7 bridges as shown on this slide, ranging from UK to Denmark, to Hong Kong, and then to Brunei. So Berry Lane Viaduct, and I'll just show you just a couple of slides. This is a bridge that was done across the M25 motorway in England back in the 1970s. And it actually goes across a wooded valley. Wooded means there are lots of trees. There are very nice houses, and the people walk around. And actually, the local people basically did not want a bridge here. So we had to find a way to build a bridge, but also at the same time to hide the bridge. So you see on this slide over here, it is a tabletop with some precast beam, and you see over here very slender columns. The idea of this column basically was that the columns, it was going to be a new motorway bridge in the middle, and then the railway bridge on the side. And the issue really was how to build 2 new bridges next to the old bridge, so there was some kind of visual compatibility between them. The span is quite modest, it's 152 meter. But you can see that the old bridge was a balanced cantilever and there was a curved soffit. So the first thing we said was that the 2 new bridges, both the road bridge and the railway bridge, should also have a curved soffit. Actually, when we came on board, they were going to have just simple straight haunches. So it took a while to convince the road authority to also have a curved soffit. Then this is the railway bridge. And you can imagine that a railway bridge, a box girder is a good solution for a railway bridge because it's very stiff. You need to make sure that the deflections are kept within a reasonable limit and that you also take care of the vertical acceleration. Now the old road bridge had spans of 40 meter, which is actually good also for a railway bridge with a box girder. But what we could then do was that the road bridge could actually have spans of 80 meter. So the idea was that the columns of the new road bridge and the new rail bridge would align with the columns of the old road bridge. And you can see over here that what was done is a balanced cantilever with a push launch approach. But the depth of a girder for a railway, for the country, this is something like 14 meters. It was very deep. And the question was how to make it look visually light. You can see what we did over here. We actually opened up the support. We also had a V section at the bottom of the soffit. And what that allowed us was to get something like this, where you have like 4 hands lifting. You have a V that then becomes flat in the middle. And you can see from this slide, hopefully, that you get a dynamic feel to a high-speed railway. So the road bridge, you can see behind it, just a very standard ballast cantilever. But you can actually take the structural design and then make it from a visually interesting by giving it a form to it. And you see on the next slide, this is the model, and this is the actual bridge. So very slim, very thin, and it actually has become quite a landmark in this particular area. So again, this is where one can take the engineering requirements, take the visual requirement, take the context, and then create something that will be of interest. I then jumped to a bridge that we did in Manchester in UK. And this bridge is in a very, the bridge is over here. This is the city center. There was an underpass going to the airport. This is a very run-down area. And this road here, which used to be a road, got cut off when they built the underpass. And actually that divided the community. So the local authorities wanted to rejuvenate this area, or improve the look of the area, and they wanted a landmark bridge. Now, as you can imagine, any landmark bridge needs to have something above the deck level to bring your eye to the bridge, so that it actually becomes a landmark. If you just have a flat bridge, then you can't see it from a distance. So the issue for us was what to do, because there's a road underneath, and we wanted to recreate this road. So we came up with the idea of a diagonal arch. And just for the interest of it, this is the first diagonal arch bridge in the world. A lot of people have copied it. I've seen this variations of a diagonal arch in many parts of the world. And in some places, it's been done for no particular good reason to me. But for here, you can see that you have a road underneath and a road on top. And what that meant is that if you put a diagonal arch, you could have an arch in 2 directions. You can have an arch when you're driving along the road. You can also have an arch when you're driving along the road on the top. And there was some sort of interesting engineering requirements. It was a very thin arch, and there was the issue of the von Mises effect. So we actually filled the top of the arch with concrete. Now, in China, they are doing a lot of concrete-filled arch bridges, but this was an early example that we did in the 1990s. And from an engineering point of view, you can see something interesting happening. Because we have cables going in only one direction, you have a horizontal bending moment in the arch, which then meant that we could actually have a wider arch width at the top. So this is a view when you're going along this road, and this is the view when you're going along the other road. So this is a interesting example where a form of the bridge is satisfying the architectural and visual requirements as well as the engineering sort of requirements. I then jump across to the horizon crossing between Denmark and Sweden. And this was a bridge that was between Malmö in Sweden and Copenhagen. And you can see you've got the Baltic Sea over here, and the water just comes into the Baltic. This is a very ecologically sensitive water. So on average, if the water enters the Baltic, on average, it takes some 70 years for the water to go out again. So it's very saline, and the issue was that we must have the least blockage of the water, not more than 2% of blockage for the water to flow into the Baltic and then come out of the Baltic. So in a design competition in 1994, this was the treaty between Denmark and Sweden, and the reference scheme was a straight alignment. There was an artificial island and a submerged tunnel. The reason for the submerged tunnel was because you got Copenhagen Airport very near, and you could not build very tall towers. So in the original reference scheme, they had 2 cable stay bridges and just a single level deck. So this is the approach, this is the main bridge, and that was the immersed tunnel. So as we said, this was an international design competition, and in the competition you had to do a design keeping the reference condition, but you could also make an open proposal. So what we did, first of all, was to introduce an S-curve. Now, if you're driving across a big expanse of water, if you just have a straight bridge, it's actually not very interesting, and you can't really see the bridge. You can only see the towers. But if you have an S-curve, you can have differing views of the bridge. So that's what makes it sort of interesting. But what we did was to replace 2 navigation bridges with 1 single navigation bridge and put a double-decker bridge. So you put the road on the top and the railway underneath. And this is to demonstrate in our competition that if you have an S-curve, you can see different views of the bridge from a distance and as you come sort of closer. We were lucky to win the design competition, but in the end, we had to, after detailed environmental studies, we had to actually compromise and just have a C-curve, but that still gave us interesting views. So the bridge is 2 kilometers of tunnel, 2 kilometers of artificial island, and then about 9.7 kilometers of bridges. So as I said, we changed the single level into 2 levels. You put the road on top and the railway underneath. In reality, actually, there are many bridges in the world that carry road and rail, and they also adopt a double-decker solution. And the double-deck is good because it means that you have a much bigger stiffness, you have a much higher moment of inertia, and means that a double deck can then take care of the vertical accelerations and the deflections, and that actually means that we can make longer spans. So by making it a deep thing, we could use 140-meter spans, and what that meant was that you would have minimum obstruction to water flow. So had we had shorter span, there would have been more obstruction. But by making longer span, we actually cut down the obstruction to the water flow, which was quite important. And then to continue with the same thing into what we did the cable stay bridge, we had the same section, but then we had outriggers to have the stay cables. And that meant that we could continue the truss form through the bridge, through the high bridge. We can have half arrangement of stay cables. And the half arrangement was very deliberately done so that the diagonals of the truss was actually aligned with the inclination of the stay cables to give it basically a visual compatibility. And here you can see on this slide, we have the main truss with the stake cables coming down, we have a bracket coming, and the whole thing is done in a way to make it very neat. And then the tower, a lot of stake cable bridges, you know, have cross beams at the top. But cross beams are difficult to build, and they take some time. So we had a freestanding tower, and the center of gravity of the load is then done on the center of gravity of the cross section. So you can have different widths, different dimensions, but you always have the load coming down the center of gravity. And that meant that, again, you have a clean look, I would say, what I normally say, the Swedish look or the Danish look, and then you have the outrigger stake cables. But once again, you can take the construction methods to help you to get the form. So this is the Swanen, the floating crane. It could lift up to 6,000 tons load. So whole precast hollow columns up to 50-meter high could be precast in factory conditions and then brought to the site. And you can see on the next slide is the caissons. We were lucky over here that the water is not very deep and sandstone was at a shallow level, so we could use spread footing. But it gives you the idea, these are the people down there, and that's the size of the of the central tower. So the construction method was to build the caissons in a dry dock and then float them out to site. And here you can also then see a 140-meter span being put into position by this floating crane. So the design of this is driven by construction method, is driven by railway requirements, is driven by trying to provide the least obstruction to the water flow. And then this is shown the last span being erected on 14th of August 1990. So that's the finished job. Simple, clean lines in the open environment, view from the bank, and then there is an aerial view. So the design for long span bridges, what we did, then I will jump from there to what has been in the press very recently is the Hong Kong, Shanghai, Macau bridge. And this bridge links, this is Hong Kong Island, this is Zhuhai on the west side and Macau on the south side. And this is the Pearl River Delta. The distance from there to there is approximately about 50 kilometers. And what is the reason for this bridge? Hong Kong, as you know, is now part of China, but is still independent. But on the east side of the Pearl River, there's been a lot of development. And the west side has been sort of left behind. So both the Hong Kong government and the governments of Zhuhai, Macau have wanted the bridge to link the west and the east side, which would actually help in the economic development of Hong Kong, which means that we can get traffic coming to our container port, you can get traffic coming to the international airport. And the bridge is shown over here, is that from there up to there is something like 50 kilometers. There is about 23 kilometers of bridges. There's about 4.5 kilometers of immersed tunnel at this location, and then there's a bridge. Now, similar to what happened for the the Copenhagen to Malmö bridge, we could not put a long span bridge here because of the airport height restriction, because the aircraft that's their flight path. So there are 3 navigation channel bridges, and once again there was an issue of not blocking the water in the Pearl River estuary. because this is very ecologically sensitive waters. And to do that, we have actually again made longer spans, up to, in this case, up to 110-meter approach spans, and then buried the pile caps. So by burying the pile caps and having single columns, we actually reduce the sort of water blockage down to the minimum that we can. So these are 3 lanes and a hard shoulder, very wide boxes. So that's the final configuration for the approach. It's a composite deck, and then we have the longer span, which again is 110-meter span orthotropic box girders. This is on the mainland side, and then on the Hong Kong side, we had the typical box girders of 70-meter. But from bridges point of view, the cable stay bridges were the most interesting, and each bridge, there are 3 of these. Our client wanted to have something sort of unique. So on the Kingshaw Bridge, we have what is known as the Chinese knot. The Chinese knot is a good luck symbol, and that has been used on this particular bridge. And on the next cable stay bridge, in this Pearl River, we have pink dolphins that are an endangered species. And the idea here was, first of all, to safeguard the dolphins, but to also have a dolphin motif. So these are cables with the shape of the tower, trying to make it as if so dolphins are coming out of the water. And the one that is my own personal contribution that has lasted is the Zhuzhou Bridge. And what I wanted to do was to have some kind of a nautical feel to the bridge, trying to make this like a mast of a sailing boat. So I had the main tower and then a kind of a backbone to the tower, and then these are the initial sort of sketches. And the design, again, is simple. It's a concrete tower with a steel backbone, and either using a orthotropic box or a composite box. And these are the initial studies, if just a single tower and then 2 towers. But the shape of the tower actually also had a structural advantage, because by actually introducing this back member, we found that the tower was stiff enough so that we did not have to have an intermediate anchor pier. You will see a lot of cable stay bridges where in the back span there you have like 2 anchorage piers, one at the movement joint and then one intermediate. But by putting this stiff tower, we actually did away with this obstruction in the back span of an anchor pier. So that's the final design with a central array of cables. This is a architectural rendering of the bridge. You can see there is no intermediate anchor pier between the main tower and the main anchor pier. That's another architectural rendering. And I thought I might show you an overall view of the whole bridge. So this is Zhuhai, that's Lantau in Hong Kong in the distance. You can see the 3 bridges. And then this is Zhuzhou Bridge. And that is the actual reality of the completed bridge. Now for me, this is a very interesting bridge because a long length, and then you're trying to create something that is visually interesting, because the bridge can be seen from the air when people take off from Hong Kong or from Macau. It can be seen from the sea, and it can be seen from the land. And so the idea was that from each visual location, the bridge should look interesting. I then jump back to Europe and to Scotland. It's a bridge that we have just completed called the Queensferry Crossing in Scotland. And for those of you who may not have gone to Scotland, this is England down here, and then we have Scotland up there. And then we have the Firth of Forth estuary, and we have a bridge going across the estuary. And this is a historic location because at this location we have the railway bridge that was completed in the 1890s, which is this cantilever bridge. There is a suspension bridge that was built in the 1960s, which is also shown over here. And the question was, why did we have a new bridge? And the reason for the new bridge is that the existing suspension bridge, we found that the wires were breaking. And at the rate at which the wires were breaking, by 2019, all traffic would have been stopped. So for the last 10-15 years, the Scottish government has been wanting to build a new bridge. Now, back in 1992, they did think about a bridge. And had the bridge been built in 1992 or 94, it would most probably have been a suspension bridge like this. Because at that time, the longest cable stay bridge span was only like 450 meters. We took part in a little competition to be appointed, and the previous engineers had actually had a pyramid-type towers, and this was in 2006. So when we came on board, the idea was to actually have a 3-tower cable stay bridge. And there is a rock over here known as Beamer Rock, on which you could actually put a tower on it. And we agreed that it could be 650-meter spans. But the question was how to build a new bridge that would be in this, what is now a UNESCO World Heritage Site. So we wanted to have a bridge that would be visually compatible with the old railway bridge and also be compatible with the suspension bridge. So this comes back to, I will talk about the 3-tower cable stay bridge and what happens with the central tower. Now, this is a well-known phenomena of a suspension bridge cantilever bridge, where you have cantilever, then you have load in the middle. And just a little recap on how a cable stay bridge works. A lot of you I know already know it, but the way a cable stay bridge works is that under dead load, after pre-stress, there are no bending moments in the cable, and then you also have a tower that has got sort of neutral bending moment in it. Just to remind you, if you have a 2-tower cable stay bridge, when you load the middle, then you have this anchor, the end cables are actually anchoring it down. And when you load the side span, you're actually de-stressing the side span stay cables. But the tower is essentially quite stopped from movement because of the anchor pier over here. But if you have a 3-tower cable stay bridge and you have a central tower, say of the same dimensions as the side tower, then you can see that there's a major difference in the deflection. So a 2-tower cable stay bridge, you get that kind of deflection. If you have a 3-tower cable stay bridge, this central tower does not have any anchors over here, so it gets a large deflection, and you get also then a large deflection in the deck. Now there are solutions for this, and I'm sure some of you know these solutions. You can put an intermediate anchor pier. You can connect to the top of the towers. You can do a cable from the top of a tower to the intersection of the side span tower, or you can actually cross the cables. And we could see why the previous consultant had probably thought about a diamond-shaped tower like this based on the re-Interion bridge. But actually, there was no need to have that kind of tower at this particular location. The other solution has been done is to connect from the top. This has been done for the Tingkau Bridge in Scotland, sorry, in Hong Kong. But this is like 450-meter span. And I'm not sure that it is particularly visually pleasing. It looks very odd to have that anchor cable. So what we did was we said we will go down the crossing cable solution. We did some parametric studies, and we found that after you had crossed 6 cables, you could actually bring the static deflection of the deck by crossing 6 cables to the same as for a 2-tower stay cable bridge. Also, we could reduce the bending moment in the central tower by crossing the cable. So this is for a single span cable stay bridge. This is the flanking tower bending moment, and this is the central tower. So by crossing the cables, we can reduce the bending moments. Similarly, by crossing, you can see the blue is with the without crossing stay cables, the red is with the crossing. So by actually crossing, but in effect, excuse me, crossing cable makes it behave like a truss. So by crossing the cable in the middle, you can actually detension the side span cables, and that would allow the deflections with crossing cables and without crossing cables. You can see that with crossing cables we can reduce the deflections a lot. But for this particular bridge, if we did away with a pyramid tower and have a very slim tower, we also reduce the amount of foundations. So once again, it's trying to emphasize that the form is actually following the function that you require for the bridge and how to minimize the cost. So this was the final preliminary general arrangement. We then looked at what kind of that. So after saying it was the cross cables, we looked at the functional, the deck type, the tower type, the approach bridges. We looked at a number of options where you can have a central tower, have one deck or split decks. You can have sort of ladder decks. You can have tower legs going on either side of the deck and have one single box. We also looked at, again, ladder deck with boxes and with eye girders. And then saying, what is the different kinds of tower forms and what is the kind of deck that you can do with it and what kind of cross section. So you can see there's a range of ideas that you could do all with a cross cable solution. And then looking at the graphics and saying, how does the new tower feel against the other 2 bridges? So the suspension bridge has quite slim towers. You have the cantilever bridge over there, and this is a diamond tower. You can have a variation of a diamond tower. There's an H tower, another A-type tower, and then just a very slim monopole tower. And you can see immediately that the monopole tower has the least visual impact on the other 2 bridges. It will not dominate the other 2 bridges visually. And then looking at aerial views of a diamond tower, A tower, different things. And once again, you can immediately see that a monopole actually fits in visually quite well with the other 2 bridges. So that was the final scheme, the monopole tower with a single box girder. I won't go into the approaches. For the final design, we said you can either have an orthotropic deck or a composite deck, and that's the final solution. But there were some other interesting features that traffic used to be stopped on the old bridge. We have put windshields, but these are windshields with very clear acrylic. There's nothing more exciting than going across a bridge and then looking at the countryside. So this is very deliberately done. So wind tunnel tests were done to make sure that double-decker buses do not fall over. And then we also have low height lighting. We didn't want to have high lighting. These are low height lighting. So again, we are marrying in the windshield with the lighting with the barrier. So this is the final design. There were some changes. So that's the main deck. These are the approaches. And the decks actually came from, were manufactured in China, in Shanghai, and then shipped to Scotland. This shows the decks being taken off. The concreting works were done in Scotland. And then this is showing some erection of the balanced cantilever erection. Some more construction shots. And this is the view and the approach. We've had nice sort of V-shaped piers to take the two single box girders. And then the final view, and I hope for some of you who may want to make a visit to this area, you will see you've got three bridges of three different centuries. So that's the 19th century, 20th century, and 21st century. Each one of them a sort of progression on the type of bridges. Lastly, let me then go back to East Asia and to Brunei. And the people who may not know about Brunei, this is on the island of Borneo. Brunei is a small country which is got two parts. One is the western part and the other is the eastern part. And then there's a bay, and in between you've got Malaysia. So it took something like, so these are the borders. If someone wanted to drive from the central business district of Brunei to Temrong, it would take them something like 4 hours to come around like this. There are two border crossings. But if you build a bridge, then we could cut the journey time down to about half an hour. So this is the final design. This is similar to Hong Kong, Shanghai, Macau. Similar. This is it's about 30-kilometer bridge. We got 3 kilometers of tunnel, 14 kilometers of marine viaduct, 2 navigation channel bridges, and then a viaduct across a swamp forest. And shows over here the tunnels, the 2 cable stay navigation bridges, the marine viaduct, and then the Temburong forest. Another issue over here. So similar to horizontal crossing, similar to Hong Kong Shanghai, we have actually introduced an S-curve to give it visual interest as drivers go across. And seeing over here again, you can see the S-curve and then going towards the forest. So what were the design issues over here? Basically, this is in very shallow water. I can see from here to the estuary, and it is very wide but very shallow. And you have very soft clays, and you can see me standing over there and, on this boat at this location. And it's also a seismic area. And the same issue again of not wanting to block the water. So the solution that we have is a very simple solution in that we put precast spun piles. We put pile caps this time above the water level so that we had least obstruction to the water flow. We use typical modules of 300 meter and then use high damping rubber bearings to reduce the seismic load onto these vertical piles, and then two simple boxes. So the construction is driven by the requirements over here. And then in order to have access to do the piling, we have actually done dredging along here to create access for the piling rigs and also for sort of delivery. And this shows the pipe for doing the dredging along this 14-kilometer length. So the marine viaduct itself, they have created a factory on site. This shows the yard, it shows the inner formwork, and it's a full span launching. And the reason for doing full span launching is to really to reduce the construction time, because it's a very short contract of 45 months. So these are whole spans of 50 meter. They were then taken out by barge to the site location and then erected into place. And this is again what I say is a world first. This is the first time in the world that two full span girders are erected simultaneously. You can see from here, you have this girder was designed in UK, manufactured in China, and you lift two girders at the same time. What it means is, effectively, we are erecting one girder per day. And that is how the time was reduced in order to meet the contract period. This shows a view of the deck about 3 months ago under construction. Now then talk about the navigation bridges, which you might find. So there are two navigation bridges over here, one at Brunei Bay and one what we call the Eastern Channel. So here you can see the view. Basically it is one single tower with a navigation channel and then two towers with a navigation channel in the middle. And Brunei being a Muslim country, they wanted something they said would be like an Islamic architecture and also a gateway. So we came up with the idea of a tower of this shape, and I'll explain a bit more, where it forms a gateway structure. But the structure itself is actually a simple ladder deck, concrete deck. So the visual interest here was how to do the tower. And what is the weight and how it would convey the unity. So there are 4 districts in Brunei. There are 3 districts on one side and another district which are separated. So we looked at, you can see that in Islamic architecture, you have a lot of gateways. In fact, some of you guys know if you go down to Granada, down in the south of Spain, you see Alhambra. And in fact, I think the next shot is possibly from Alhambra, where we also have screens and the arches. So that was the inspiration to try and do this bridge. So what we have done over here is to have 4 architraves. These are the architraves, which shows the 4 districts coming together. And that's the slot over there to say we have unified the 4 districts. So we created a kind of a gateway that is symbolic. But in engineering terms, it's actually just a diamond tower. So it's the main member over here coming down. So it's basically a diamond shape. And the construction is hollow legs, and then up at the top, we have the connecting walls. So that is, once again, looking at a certain location, looking at the culture of a certain place, looking at what is the engineering and the geological conditions, and then starting from a blank sheet of paper to say, well, what actually fits? So coming back to the same idea again, form and function, we're trying to marry the two. So this shows very recent construction slides of what is going on. And this is a very sort of recent photograph. So for the young engineers in the audience, I mean, you may say, well, what is the future of bridges? To me, at the moment, it's very exciting. You know, we're going to see very long spans, and we're going to see long bridges in very deep water. We will see crossing, maybe Gibraltar crossing, maybe between Alaska and sort of Asia, across the Red Sea. And I think we are going to have bridges with composite and high-strength materials because we need to reduce the weight. You can already see that we are using drones for inspection and rehabilitation works. And then we may also have construction with sort of robots. But guys, the good news for the young engineers who are in the audience, if you're a designer, just remember that there will always be need for a designer. You can't have all these bridges unless someone has actually designed the thing. So if you're a designer, you need to take into consideration the environmental and cultural aspects. You must consider the client's budget. Aesthetics is very important. You need to have appropriate construction techniques for the bridge design. Then all of these can be combined in form and function for the particular site. So it's just, you know, when you're talking about engineering, you know, engineering and bridges is much more than that. So it's the cultural part, it's the aesthetic part, and it's the engineering, all that combines to come up with a bridge that is actually appropriate for the particular sort of location. So to me, I wish I was starting again. The future is going to be exciting. And thank you for inviting me to give this small talk. Thank you.